Welcome to lesson number 5. We're going to look at interpreting graphs of functions. So we have the Carter family, and they're driving to the Yukon for a family vacation. The graph represents the amount of fuel in liters in the gas tank of their car on the first day of their journey. So here's the first day of their journey, and this is showing what they did on their first day in terms of fuel use. So it doesn't show us how far they went, it just showed us how much fuel they used in a certain amount of time throughout the day. So from 0700 hours to 1700 hours. Now, first of all, we might want to look at what our scale is increasing by. So if on our left-hand side on the y-axis, we have the amount of fuel in liters. And so our fuel increases from 0 to 60 liters, and it goes up by an interval of 5 each time. And then we have the time of day, so from 0700 to 12 o'clock, so 0700, 0800, 9, 10, 11, 12. And so our x-axis, which is our time, is increasing by an hour at each interval. So let's look at the problems that we need to solve. So the graph of the journey is divided into 8 line segments. With reference to the journey, we want to explain what is happening between A and B, B and C, and C and D. So let's see what's happening at A and B. So from point A to point B is where we're looking at. And so if we look at the amount of fuel that was in the tank, there was 50 liters of fuel. And then as you drive, you consume fuel, and so you get to point B. And so from A to B, there's not much change. See, the line itself doesn't change in its steepness either way. And so what this means is that they were driving at a constant rate. And so if we look at how long they drove for, they drove from 7 to 10 o'clock. So they drove at a constant rate for 3 hours. So they drove at a constant rate for 3 hours. Now this is why something like cruise control is so nice. Because if you're driving at a constant rate, then the amount of fuel that you're using isn't going to fluctuate too much. And so this line, you'll notice, doesn't fluctuate very much. And that means that the amount of fuel there is, if they were to speed up, they'd end up using more fuel in that amount of time. And this line could start to drop a little bit faster, in which case they would end up with less fuel than the 20 liters that they have when they stop. So at B and C, let's see what's happening. At B and C, this is also a constant line, but notice how the amount of fuel isn't moving. And this happens from 10 o'clock to around, let's say 10:30. So I'm gonna go 0800, 0900, just so this is a little bit easier to see, and 1100, so 10 o'clock. So 8 o'clock, 9 o'clock, 10 o'clock, and it looks like they're stopped from 10 o'clock to 10:30. And so it looks like they took a 30-minute break. So a 30-minute break from driving. And then let's see what happens to our fuel consumption. So at 10:30, notice how our fuel goes back up. So it goes all the way back up to 60 liters. And so at this point, it looks like they refueled, so they gassed up. So gassed up, or refuel. Now, what is the rate of fuel consumption in liters per hour between D and E? So D and E is our next interval on the trip. So from here to here, we want to know what our fuel consumption is. So we started off with 60 liters of fuel. So the amount of fuel used was equal to 60 liters, and we subtract, and we end up with 25 liters at E. So if we look at where E is, that's 25 liters of fuel that's used. That means that the amount of fuel we actually used was 35 liters. So 60 minus our final amount of fuel used is 25, or fuel left in the tank. So that means we used 35 liters of fuel. And the amount of time that happened in, well, let's see here. So at time D, that was at 10:30, and so that's when they left again. It was at 10:30, and then they got to point E at 2 o'clock. So that's a time interval of 3.5 hours. So 1, 2, 3.5. So the amount of time was 3.5 hours. And so we can represent this, the rate at 35 liters divided by 3.5 hours. This is equal to 10 liters per hour. So the rate of fuel consumption between this point D and point E was 10 liters per hour. Now, which line segment represents the car being refueled for the second time? Well, the line segment that shows the car being refueled again would be the point at which, from E to F looks like they take another break for an hour, and then they drive a little bit further to point G, but then check out what happens to the gas. So they're down to 15 liters in their tank, and they bump right back up to 60 liters. So the time interval G to H is the second time where they're refueling. Now you want to calculate the total time when the car was driven. So from the total time the car was driven, well, if we look at our total trip, we have from A to I. So from A to I, and if we look at that amount of time that we go from A to I, so 0700 hours to 1700 hours, and we also have some breaks in between, and that we gotta look at the breaks that we have. So we have this 30-minute break. So first of all, this is 10 hours that they were driving in total. So 10 hours driving in total. But we have a 30-minute break where they're not driving, and there's also a 1 hour break, and that was at E to F. So 1 hour break. And if I have 10 hours and I'm subtracting 30 minutes and 1 hour, so we would have 10 hours, subtract 1.5 hours, that's going to leave us with 8.5 hours of total drive time, right? Because we got to subtract our breaks, so that's the amount of time that we're not actually driving. And finally, the fuel costs 85 cents per liter. Nice. Calculate the cost of the fuel used for the first day of the journey. So the first day of the journey, remember that they're actually driving for, well, let's look at A to B. So the fuel used, let's make a little chart. So our fuel use from A to B, and remember we had started off with 50 liters in the tank at point A, and then we went down to 20 liters. So 50 minus 20, and that is 30, plus point D to E, because we're not driving from B to C, so plus D to E. And let's look at how much fuel was used at D to E again. So we started at 60, and we got to subtract 25 from that, so 35 liters. So 60 minus 25, 35 liters. Plus we got to look at F to G. That was the next time we were actually driving, and that's right here. So we had 25, actually, 25, and we're subtracting 15 from 25. So F to G. Plus 10 liters, that's used. And then H to I was another 60 liters, and we don't use very much fuel in that last point of the trip. Another 10 liters. So 45, we get 85 liters of fuel used. Now, if we use 85 liters of fuel, the cost is going to be equal to 0.85 times 85. And this is going to be $72.25. In example number 2, we're analyzing these graphs and coming up with a scenario for each of them. So if we look at this first example, A, I have speed on my y-axis and time on my x-axis. Now when we're looking at speed and time, what we're looking at is a graph of distance. Now, we could also think about like an object that's traveling at a speed, and then speed decreases, travels at a constant speed again, speed increases, and then they travel at a consistent speed, and then they decrease again. So what we might want to do is just label A, B, C, D, E, F, G. Now, if we think about it in these time intervals, from point A to B, we have travel at a constant speed. Notice how the speed itself is not going up or down, so the speed we would say is constant. From B to C, however, the speed is decreasing. So speed begins to decrease. Speed's decreasing. I don't need apostrophe there. From C to D, speed is again constant. Is again constant. From D to E, we have an increase in speed. E to F, we have constant speed once again. And F to G, we're slowing down again, so speed is decreasing. Now this is a relatively short period of time. You could think about it as a relatively short period of time anyways that this is occurring in. And so this could be like traveling through town, right? Like you're traveling at a constant speed going 50 kilometers per hour, and then you come to a stop sign, you gotta slow down, and you start again at a pretty constant speed, and then, you know, driving through the intersection, you might speed up again, and then you might have to slow down for some reason or other once you, maybe this is speeding up from stopping, and so you're speeding up, going at your constant speed, maybe through a school zone, maybe it's 30 kilometers per hour, and then you're coming to a stop sign again. So that's one scenario that you could look at. This graph over here is a little bit different. If you look at this is just a repetitive motion. And so if we look at it overall, it looks like a pretty constant motion. So first speed picks up, and then it decreases, almost stopping, picks up again, and decreases, almost stopping, picks up again. This is what's known as pendulum motion. So pendulum motion. So this could be like your clock that has the pendulum, you know, those old grandfather clocks that I guess probably nobody has anymore. But the Newton's cradle that you know of when we've done conservation of energy demonstrations is also an example of pendulum motion. Last, we have class example number 3. We want to sketch a graph with no scale for each of the following. The oven temperature when baking a pie. So if we're starting at time of 0, if you ever baked a pie before, your oven's not automatically hot. So you have to turn the oven on, and your oven's going to preheat to a certain temperature, and then hopefully your temperature remains constant. And so you would bake your pie at the constant temperature, and then you'll take your pie out and you'll let it cool down, and then the overall temperature, even and especially if you turn off your oven after, is going to decrease. It probably won't decrease to 0 because your oven would be very cold, and probably if it decreased to 0 degrees Celsius, that means your oven is outside in the middle of winter. Next, we have Ben taking part in a 100-meter sprint. And so when you're sprinting, your speed will go through a really brief moment of exponential growth, very brief. And it looks something like this. But obviously, you can't keep that type of that rigor up, and so then your speed will kind of plateau at a constant rate, and then after a while you start to slow down, and that slowing down until you're 0, you've stopped, is a lot more drastic. And so that's kind of what that graph could look like.